Last week, you got an introduction to biomedical ontology by Irshad. I will continue this series within the bootcamps with 3 classes. Today, elements of logic for ontology. Then Wednesday, principles of realism-based biomedical ontology. And then on Thursday, a more practical workout of how you use first-order logic to develop realism-based ontologies. So there is also a 5th one, which is by the end of the month by my colleague Alex Deal, who will talk about Sparkle queries. Just as a heads up, I will ask several times whether there are any questions. When there are questions, then please ask them. But if you have an urgent question while I'm talking, please shout. I'm not very good at seeing that little hand going up somewhere. So if you need to have something addressed, immediately just shout and I will respond. So what are the learning objectives for those 3 days that I will be giving? So for today, I hope that you will understand at the end of this lecture what the difference is between ontology in the singular and ontologies in plural. That you know the difference between ontologies and other types of knowledge representation, because believe me, there is a lot of confusion about it. The distinction between concept-based ontologies and realism-based ontologies. Also that you would be able to explain the distinction between logics, logic programming and formal representation. And that you also have some idea about the logical and ontological principles in knowledge representations. So Wednesday, we will then apply the previous to the basic formal ontology, the Obo Foundry, and some bioportal ontologies. It is important that you would be able to describe how realism-based principles differ from computational principles and from logical principles, which we discussed today. And if we have time, we will also look at the ontology for general medical science, which is an ontology which has been developed underneath the BFO, but is far only in a taxonomy and poorly axiomatized. Last learning objective for tomorrow is to understand the distinction between non-realism-based ontology and how they rarely use the same set of principles. And that's very important for if you want to be able to resort to many different ontologies that have been developed independently of each other. Usually that poses many problems. And then on the 3rd day, let's get this away, we are gonna show how you will write ontology axioms in first order logic, and specifically by using a format which is called CLIF, which is Common Logic Interchange Format. So, part 1 for today, ontologies, representations, conceptualizations, and reality. Okay. The most cited definition that you will find for ontology is the one from Gruber, which he wrote in 1993. An ontology is an explicit specification of a conceptualization. That was quickly picked up by the medical terminology community, and they started to use then ontology as a synonym for formal terminology. But you need to realize that explaining and standardizing terminology is very different from explaining and formally representing the entities in reality denoted by the terms. And an interesting aspect of that paper is it has, I think by now, referenced close to 40,000 times. But I'm sure that over the past 25 years, all those references, the ones who use it as reference never read the paper. Okay? Because in there you will also see this phrase here. The term is borrowed from philosophy, where an ontology is a systematic account of existence. For knowledge-based systems, what exists is exactly that which can be represented. That by itself is already a very restricted definition of what ontology, or an account of what ontology actually is. So ontology borrowed from philosophy. Indeed, ontology is the study of what entities exist and how they relate to each other. Now, some philosophers take that to be synonymous with what is called metaphysics, and then others, they draw distinctions in many distinct ways. Those distinctions themselves, they are not really relevant for this talk. But almost they agree on the following classification. So metaphysics studies how is the world. General metaphysics studies general principles and what we would call laws about the world. And ontology is a subdiscipline of that studies what type of entities exist in the world. So it is important to understand that for studying the world, how is the world, you do not necessarily need to commit to the existence of certain entities. Okay? So if you do pure metaphysics, you don't need to worry about that too much. But if you are an ontologist, there is the extra requirement that you have to commit to certain entities. And there is a choice there. So it is the case that not all ontologists have the same, what is called ontological commitment about what exists in the world. So there can be differences there as well. But the important part is if you start to reason or to build argumentations on the basis of ontology, you need to make some ontological commitments and then stick to it and see what the consequences therefrom are. Now, a very important distinction also between ontology is between epistemology and terminology. So ontology is distinct from epistemology because that is the study of how we come to know about what exists. So in a sense, okay, it's not possible to do ontology if you don't have epistemology. But the important aspect is that once you use epistemological mechanisms to find out what exists and why you should believe in the existence of certain things, that what exists may not be described on the basis of how you discovered it, that it exists. Okay, so that's also a mistake that is quite often made. Ontology is also different from terminology, which is the study of what terms mean and how to name things. It's a very important study as well, but it is not identical with ontology. True, when you build an ontology, you should adhere to a certain terminology, but the ontology should be the foundation for the terminology and not the other way around. And I will explain that when I will talk about the distinctions between the concept-based approach and the realism-based approach. So the most important takeaway about that definition is that Gruber did not intend to describe reality. Read the paper and you will see. So Gruber worked on AI, and at that time AI was focused on closed world reasoning. He argued that ontological commitment should be minimal. Okay, while as a true ontologist you say, well, no, you need to be as exhaustive as possible, okay, within the domain that you are building your theory. He also argued that what he called shared conceptualizations must be founded on the purpose of the resulting artifact rather than based on a priori notions of naturalness or truth. Okay, so whether something is the case or not, or whether something exists or not, that was for him not important. Because his idea was, how can we make software talk to each other? How can we make robots that are running around in a room? How can we make them communicate? And robots don't need to know exactly what is in the room, whether something that they might bang into, whether it is a table or a chair. The only thing that they need to know is whether it's something, if they bang into it, will they get damaged, yes or no? Okay, so those are the important aspects. That's where that argument for minimal ontological commitment comes from. Okay, you only need to tell those robots or those agents just what they need to know to do their task. The purpose was knowledge sharing and interoperation among programs. Okay, so that knowledge does not belong in his conception of ontology, but in a knowledge base designed for the specific purpose the software program has to serve for a specific audience. So you see, it is very restricted. Okay? The modern sense of ontology, or the philosophical sense of ontology, is much broader than just that. So how do we compare the two? Okay, so in Gruber's ontology commitment should be minimal. In realism-based ontology, ontological commitment should be based on justifiable true belief. Justifiable true belief, that means it must be true, you must believe it, and you must have arguments to believe it. That is usually a definition that is used to define what knowledge is. And there are some holes that you can poke in it, which are not relevant here, but it's nevertheless a very good account of what ontological commitment should be under a realism-based perspective. So for Gruber policies, the purpose is knowledge sharing and interoperation among programs. For realism-based ontology, the purpose is representation of the generic entities that exist and the relations amongst them. So now, what are those generic entities, and do we commit there to them or no? Well, there are actually three main, let's say, divisions or views in the philosophical world. So one is nominalism. Nominalists, they say there are no generic entities in reality. There is no thing such as personhood, or no thing such as an animal or table. There are only individual persons, individual cats, individual tables, and so on. So now, of course, we see that cats look more like other cats than they look like tables. Okay. For a nominalist, they say, well, no, you might think so, but that is not the case. Each individual is its own individual. Conceptualists, at the other hand, they say, well, those kind of generalizations like personhood or cathood, they are in our minds. That actually means that you have to believe in the existence of a mind on top of a brain, right? But anyhow, so they say personhood is a concept construed in our mind that allows us to reason about persons without any particular person in mind. And that is indeed true. If I would tell you now that my cat is sleeping behind on the sofa here behind me, well, you have some idea of how that thing, which I called my cat, how that looks like. You don't know the color, you don't know whether it's male or female or whatever, but in any case, in your mind, there is currently not the image of a cow sleeping on my sofa. Right? So there is one of the advantages of adhering to conceptualism. Now, for realists, generic entities, they do exist, and they call them universals. And each particular person is an instance of the universal we call person. So conceptualism is the mainstream approach. So if you read about ontologies, or you go to the bioportal, or you go to the semantic web, it's all about concepts and classes, right? Realism, at the other hand, is what I would call the scientific approach. It is not based on what we think that there is, but in the first place, on what there is. Right, third distinction. So Gruber says shared conceptualization must be founded on the purpose of the resulting artifact rather than based on a priori notions of naturalness or truth. Okay? For realism-based ontologies, the shared conceptualizations must be founded on science and be based on truth, interpreted as best scientific evidence. So this is schematized in this way. So Gruber's conceptualization for ontology looks like this. You have what he called relevant invariants. Invariants are those things which do not change. Okay. Now think in terms of the agents that he was designing. In that context, relevant is important, right? So what is relevant for that agent, or what is relevant for that little robot to be known? So what is relevant and what is invariant? Okay, you need to express that in a language, from computer language, knowledge representation, or what else. And that language should actually give you your ontological commitment. You should only put in your language what you believe that is the case, okay, relevant for what the program or the robot needs to do. Now, but then with every language, you need to give it an interpretation, okay? And the interpretation needs actually be such, okay, that it as maximally as possible ensures that you represent in the language that what you want to represent. So if you use for your language a model theoretical semantics, okay, then you need to build models, and your interpretation can be all those models here. What you want to have is the intended models only. Now, intended models is what you want for, but you might also have unintended models. And it's not always possible when you write your language and the axioms around it to avoid that there are unintended models which come into your work. So for the realist conceptualization re-ontology, well, that conceptualization does not stand alone. Okay, that must exactly be based on reality, on certain phenomena that you observe. Okay, and now, of course, we know there are people who say it is totally impossible to know what is exactly the case, because we have our brain, and our brain might fool us, and we have our sensors, like we can see, we can smell, we can feel, we can hear, okay? But our brain does those tricks. And when we see something that is red and somebody else sees something that he has learned to call red, okay? Do those two persons see exactly the same thing? We can't know, okay? But on the other hand, there are indeed certain invariants in the sense that we have learned to talk about certain things in the same way through education, through our parents, through our teachers, right? And we all say when you bang your head in the wall, it hurts. We know what it is. So that reality, in any case, it is accessible, okay? And it is because it is accessible, we can perceive it. And then it is indeed the case, okay, that we can build in our brains concepts about what is the case in reality. But keep that in mind, okay, we will come back to that in a bit. Fourth element, knowledge for Gruber does not belong in an ontology, but in a knowledge base. Okay, what's the difference in that case? So if you think in terms of those generic invariants, for instance, that cats exist, okay, would be in Gruber ontology, but that my cat exists does not belong there. Okay, that a thing that I own is a cat, that's knowledge. Okay, realism-based ontology is kind of in line with that. Specific knowledge indeed does not belong in an ontology, but in a data repository. That together with the ontology can be used to perform reasoning. For instance, to advance science. So he also talked about the goal of the ontology, which in his specific case was restricted to communication between agents. There are other papers that have been written about purposes of ontology, and this is actually a very good one by Deneau and friends. So they looked at the literature and how people have been using ontologies over the past so many years, and they came up with these 6 goals and purposes: investigating a domain, representing a domain, enhancing collaboration, supporting data-related processes like searching, indexing, merging, and so on, supporting ontology-related processes like comparing ontologies, merging ontologies, using them, aligning them, and finally providing reasoning facilities for specific applications. There is a division, okay? So these 4, that is actually using ontologies for people, to let people do better things or do things better. These 3, they are actually for computers, okay? And the 4th is actually something that is relevant for both people and for computers. And that gives actually a nice distinction on how to classify, let us say, certain representational systems. So you have on one axis, you have the direct usefulness for people, and you have on the other axis the direct usefulness for computers. So you see that terminological systems, okay, they are primarily on the left side, okay? They are very useful for people, but they are not so much useful for computers. Okay. Knowledge representation systems are in the middle, okay? Realism-based ontologies are there, okay? The right hand. So they are directly useful for computers. That's why you need to express them in a certain logic that machines can reason with. But it is, on the other hand, rather hard for people to use them. And it suffices to look, for instance, at the, by now, I think, 1,300 different ontologies that have been submitted to the bioportal. Less than 10 contain mistakes. Okay, the large majority of them is full of logical and ontological mistakes. Okay, why is that? Because the proper tools have not been used to design them, or people have not been careful enough about designing their ontologies. And an additional problem is that actually, because of the popularity of the word ontology, all those different things here are called ontologies. So whenever you read a paper about ontology, try to find a definition in there, what they exactly mean to it. Usually they will not give it. They will give Gruber's definition. But if you read what they are writing, okay, so it might be about the terminology, or it might be about the knowledge representation. In rare cases, it would be about realism-based ontology. If it is the case, okay, then it would be explicitly said so. So now, how is that schema here? So we started in that schema, which is a very nice schema that has been built by Nicola Guarino to explain how actually the relationship is between reality and ontologies and how you get there. Okay, so for Guarino, a bad ontology is when not all ontology models that you want, so all intended models, when they are not included in what you get. A good ontology is one in which all intended models are in there, but you might have still unintended models that are in there, okay? But as long as you have everything that you want in there, then you are considered to be good. Otherwise, it is bad. Ideal is, of course, that you have only intended models and not one single unintended model. Second thing is, of course, now, what do you want to be in the ontology? Well, conceptualists and the Gruber kind of approach is, well, what we do in our ontology, we put those conceptualizations in there. Or at least, sorry, I should correct that. You can't put the conceptualizations in there. You can only put a representation of the conceptualization in there. In realism-based ontology, you don't want to put a representation in there of your conceptualization, but a representation of what is truly the case. Okay? That is a difference. It might be subtle in a certain sense, because you can't go here directly from there. You need to go over your conceptualizations. Okay? We have our brain, and that's what we need to work with. But you should not represent what is in your brain. Yeah? You should represent that what is in your brain is about. Okay? So if you are further interested in these issues here, these are actually three very good papers that describe some of the problems and things that you need to be aware of. I'm not going to read that for you. You will get the slides afterwards, so please have a look at them. So are there any questions about what I talked about thus far? No? All right, let's then look at part 2, ontologies and logics. Okay. So again, that schema here. If you go from here to there, Okay, from reality to conceptualizations, you should apply ontological principles. And that's what I will discuss tomorrow. Okay, what we will discuss today is actually the elements about the language here and the logical principles that you are using to use the language appropriately and get, if you applied your ontological principles adequately, okay, the sorts of ontologies that you get. Okay, so this is for today. This is for tomorrow. So what is a logic? Well, a logic is a formal or informal language together with a deductive system, so a reasoning system, and or a model theoretic semantics. There are different kinds of semantics. Model theoretic is one which is most often used. Now, the language itself has components that correspond to a part of a natural language, just like English or Greek. The difference is that it is very heavily regimented, while that is not the case for what we call natural languages. So why do you need a deductive system? Well, that's to capture, to codify or record arguments that are valid for the given language. And the semantics is there to capture, codify, or record the meanings or truth conditions for at least part of that language. So let's start with propositional logic. That's the easy one, elements of which I already got. I'm from Belgium. You might have heard that on my accent when I was in 10th or 11th grade. Now we got already some courses in propositional logic. So let's look at the language and the semantics of propositional logic. So a well-formed formula is either atomic or composed following certain compositional rules. Okay? Atomic formula, they stand for propositions. They must either be true or false. For instance, John eats too much, or John has a normal BMI, or John is careful. So in propositional logic, all such statements like this, you represent them simply by a letter. And now you have connectors with which you can combine those letters. You have connectors for negation, for conjunction, for disjunction, for material implication, so the if-then statements, and also for big conditionals like the if and only if. Now, of course, you can express those connectors in different ways, and here on the right-hand side, you see different symbols that are used by different authors and scholars, depending on their choice. So usually they are not mixed. When you read the paper, people will, for instance, for material implication, consistently use this arrow or consistently use the double arrow. But if you go through another paper, then they might use this. Another one might use this, and so on. Might be a little bit confusing, but that works itself well out once you get familiar with reading that stuff. Now, then the deductive system for propositional logic, it's quite simple. It's truth tables. Okay? So all those tables here, but oops, what do they express? So in the case of logical negation, you only have a P and a not P. So if P is true, not P is false. If P is false, then not P is true. For logical conjunction, you need to work with two. So you have P and Q, and now you have P and Q. So when both P and Q are true, then P and Q is true. And in all other cases, P and Q is false. It's not too hard. You can see it on the other tables what is the case. There are anyhow some things that you need to be careful at, and that is sometimes surprising. So that is this one here for the logical implication. Okay. For the logical implication, you see that if your premise is false, then independent of whether the conclusion is true or false, the statement is true. Okay, so this is actually leads to the saying that from erroneous premises you can prove everything. Okay, So you need to be careful with that. And also when you look in ontologies, that is where most often the mistake is made, okay? By working with logical implications, where in many cases, or when you are writing your axioms, okay, when you forget that your implication is true, even when you have a false premise there. So keep that in mind. Based on that deductive system, okay, you can design laws, and many laws have been built. For instance, if you have A and between parentheses B or C, that is equivalent with A and B or A and C, and so on. These are just 6. If you are a logician, you know probably 50 by heart of them, and there are way many more. So here are a couple of references. If you are interested in this, you can find actually an exhaustive list of all the rules or the laws like that you can use when you are trying to solve puzzles by means of propositional logic. These laws can be used to solve puzzles, but also the truth tables themselves. So let's do a little exercise, and I now need your collaboration, right? So if I tell you the following, if John eats too much, then he does not have a normal BMI. So BMI is a body mass index. It's not biomedical informatics. If John is not careful, then he eats too much. John has a normal BMI. So these 3 are given. The question is John careful? What do you guys think?
Yes, he is careful.
Okay, so let's look why. How do we do that? Well, we translate the sentences in propositional logic. Okay, John eats too much, A, John has normal BMI, B, and C. So then we represent what is given. So if John eats too much, then he does not have a normal BMI. You represent that as A implies not B. The next one, not C, implies A. And then John has a normal BMI. It's simply your B. Okay. What you then need to do is to determine the truth value of the conjunction of those 3. So which is this formula here. Okay, there are 2 ways that you can do that. One is with tables. So you start what is there, you know that this is true, okay, and you know that this is true, and you know that is true. And then you start your, and you know that B is true here, okay, that's mentioned twice. So then you can say, if B is true, then not B must be false, okay. If this is true, and the consequence is false, then it's this case here, then you know, okay, we must have false in the first place for the premise. If that's false, it's of course false there as well. Okay. Again, the logical implication here, the one false, oops, I lost it there. Let's go back. Okay. One false, so your implication must be false. The implication is false, that must be true. And finally, indeed you have it, C must be true. Okay. Well done. You can do the same thing by using the laws. And by using the laws, it usually goes quicker. And the more laws you know, the more quicker it goes. So in that case, you label those different assertions here, like G, given 1, given 2, given 3. If you know this rule here, okay, with not A, gives you the result not A by combining G3, given 3, and given 1. Okay. You label that as given 4, and then you use this formula, in given 4 in combination with given 2, gives you C as immediate answer. All right, so another exercise. Solve this puzzle. Everybody who eats too much does not have a normal BMI. Everybody who is not careful eats too much. Everybody has a normal BMI. Question, is everybody careful? What do you think?
I think everybody's careful.
Everybody is careful. Is everybody careful? In reality? No. Has everybody a normal BMI? By far not. Right? Nevertheless, given all those elements, your reasoning is true. Okay. So there you see immediately that logic has not necessarily to do with what is actually the case. Okay. That brings you in the validity and the soundness of arguments and so on, things we are not going to deal with. What we are concerned with here is simply when you look at the logic, you look at the rules, what can you deduce? And indeed, it didn't make any difference whether we just use John here or whether we used everybody. Okay, in the previous slides, you saw it was John here instead of everybody. So the reasoning stays exactly the same. Now this one. Everybody who eats too much does not have a normal BMI. Everybody who is not careful eats too much. John has a normal BMI. Is John careful?
Yes, John is careful.
Okay, can you explain your reasoning?
Well, John is part of everybody. So all of the things that apply to the first two premises would apply to John also.
Okay, so how do you represent in propositional logic that John is accounted for in everybody?
I don't know. John would be a variable in the.
In propositional logic, you can only have assertions. Okay, you can only assign letters to assertions.
I'm not sure.
Yeah. Well, I'm very short. You can't. So that's one of the restrictions of propositional logic. This puzzle cannot be solved by using propositional logic, okay? Because there is indeed no way. So within what the let's call it the grammar of the language allows you to do, there is no element in the grammar that allows you to link John to everybody. Okay, so that's the problem for propositional logic. Okay. Therefore, we need something else. Okay, and one of the things that we can use then is first order logic. Okay, which is the next topic. But before that, are there any more questions about propositional logic? Well, okay, let's look at this. First order logic is sometimes also predicate logic because it has primarily to do with how you write your sentences and formulas in there. Okay, so it is similar. It's based in a sense on propositional logic, but with predicates, variables, and quantifiers. Okay, so when you didn't have variables and you didn't have quantifiers in propositional logic. So a predicate is a proposition that some property holds for some entity or a relation between entities. For instance, everybody eats too much in propositional logic would be A. In first order logic, it would be A stands for eats too much, and now you would write AX. You have quantifiers. The all is like that upside down A, and the sum is that flipped E from existence, and the A is from all, right? But they flipped it because otherwise it might interfere with the variables that you can give. So you would represent for all x AX when you mean everything eats too much. And you would write there exists an x such that AX when you mean something eats too much. Okay. Now, why do I say something? That is because we are here completely neutral about what the x exactly is. So if you would want to say that everybody eats too much, okay, you will also need to say that an x needs to be a person, okay? And then your expression would be, for all x, if it is the case that x is a person, then x eats too much. So within first order logic, the user defines these primitives, okay? So constant symbols. That's what I'll call the individuals in the world. For instance, BFO or John or the number 3. Now you have function symbols, okay? Function symbols, they map individuals to individuals. For instance, the author of BFO is identical with Barry Smith. BFO stands for Basic Formal Ontology. And now you have predicate symbols. Those are mappings from individuals to truth values. For example, that 5 is greater than 3 is true. That Barry Smith is smart is true. Okay, so those are the things, the primitives that you define as a user. They do not come with the language, but you can express that in the language. So the primitives of first order logic itself that come with the language, so are the variable synonyms like X and Y, and then the connectives, which are actually exactly the same as in propositional logic. The not, the and, the or, the implies, and the if and only if. And then the, I should get rid of this bloody thing. Oh, there, that's better. And then the quantifiers, okay, the universal quantifier and the existential quantifier. So they come with the language. Of course, you need to look at the truth values for quantified expressions, okay? Just like you have to look at the truth values in propositional logic for your combined expression. So if you have a statement for all x, ax, so that is true when ax is true for every x, and false when there is one x, or at least one x for which ax is false. For the statement there exists an x such that ax, okay, there is an x for which ax is true, at least one, and it is false when ax is false for every x. What you may not forget is that those statements, they are intended to be in what we call the open world, okay? So they should be generally true, okay? And not just for what is in your database, okay? If you have a database and your logic, for instance, is working on that database, and you ask the system, are all cats black? And in your database, all the cats are indeed black, the truth value of that statement, all cats are black, can actually not be determined from the database. Okay? It has to be true in general. If it is not true in general, then you should not make that assertion that all cats are black, even if all cats in your database are black. Okay? That's the distinction with open world and with closed world reasoning. First order logic is open world. You have flexibility in predicate formation. Okay, so imagine that you want to represent some people eat too much. Okay, so you can say, okay, there exists a person X, and X eats too much. Or you can write, there exists an X is a person, and the predicate eats hold between X and too much. Or you can write, there exists an X and there exists a Y, and X is a person, and X eats Y, and Y has the quantity too much. Okay. Again, this is up to you how you do that. However, they are not equivalent. Okay. And if you look with an ontological eye to it, okay, then they are based on a different ontology. And then ontology used here in philosophical sense. Okay. So here, for instance, you commit to just one entity, right? You only commit to the entity X. Here you commit to two entities. So you commit to the existence of quantities, while you do not do that explicitly in this way here. Okay. So now the important part is to build an ontology using first order logic. Okay. And if you are a realist ontology, then you should make your choice on the basis of the ontological principles that are described, for instance, in relations in biomedical ontologies. So that will help you in deciding which one of these representation is actually the most adequate one when you want to design your ontology on realist principles. You also need to be aware of certain ambiguities in the language. And one of the most difficult things in using first order language is to express in the logic what you want to express on the basis of natural language. Okay, so take a sentence as every patient has some provider. Okay, so how would you represent that? The problem is that sentence is ambiguous. Okay, so it can either mean, if you look at it with a logical representation, that for all x there exists a y, such that x is a patient of y. Okay, so this actually corresponds with this, that every patient has some provider. Okay, this one here, there is a y, such that for all x is the patient of y. Okay, this means there is some provider that provides for all patients. Now, in other language, we glue over those things automatically. Okay, so nobody actually, when you read this sentence, will give it this interpretation. Okay, because everybody knows at least 2 or 3 providers, so you know that it can't be true. Okay, that there is one provider who provides for all patients. Okay, but you can easily make this mistake, right? If you are translating this, okay, and you use this representation of that because you do not understand how those quantifiers exactly work, then you are representing something that you did not intend to represent. And if you do that, then you get those unintended models. All right, that's so far for first order logic. Questions? So tomorrow we will deal with those ontological principles and see how that really fits into the logical language here of first order logic. And then on Thursday, I will guide you to some practical things on how to apply both together. So if there are no questions, then I will continue with the talking about description logic a bit. So description logics are extremely popular. Okay, so it is a fragment of first order logic. They come in many varieties with many names and many different characteristics. The important part is that they are all decidable. So description logics are actually designed to make your logic or any statements in the logic decidable, which is not the case for first order logic. That is not a problem that it is not the case for first order logic in most cases, but sometimes it has some nasty consequences. Okay? So what does it mean to be decidable? The logic is decidable if there is an effective method for determining whether arbitrary formulas of the logic are logically valid formulas. Okay. So first order logic in general is not decidable if the signature, and by signature we understand so the list and description of non-logical symbols, if it includes equality and at least one other predicate with 2 or more arguments. So if you have that in first order logic, then you are not decidable. So there are limitations, okay? So there is quite a bit what you would want to represent in a description logic, but yeah, that you cannot express, because if you would express it, then your logic would not be decidable, and you want to have precisely a logic which is decidable. That's why you use description logic, okay? But despite these limitations, and because the use in the web ontology language, OWL, it became actually the most popular one. So what are the relations a bit between them? So first order logic goes actually here. Okay, if you take that, now you see description logic, they cover this part, And now you have what they call horn logics programs. So those are, it's also a subset of first order logic where you can have only one consequence for each assertion. So you cannot have statements in the sense as if A and B, then C or D. So that is outside the horn logics. You have description logic programs, okay? Description logic programs are not the same thing as description logic, but they combine actually horn logic with description logic to do something special. And now you have few logic programs, they add certain things which are not logical, and I mean not logical in the sense as which is not pure logic, but which add other elements to it, like certain heuristics or negation as failure. For instance, that means actually, okay, if we don't find something in the database, then it is not true. So you violate in that principle, in that way, the open world principle. But if your logic has to reason just with your database, then that's not a problem at all, okay? And other things such as procedural attachments. A disadvantage of description logic is also that you cannot have, for most of them, okay, predicates with more than 2 arguments. So that's why if you look at ALF, for instance, you will always see that your relations are binary, okay? Now, there are a few exceptions where they have been able, by constraining certain things in certain ways, so that you could use ternary relations and still are decidable. But those are really exceptions within the description logics. So what are the essential components of a DL? So they use a different terminology than in FOL. So you have FOL first order logic, okay. An A box, for instance, Father John, which they call concept assertion, means John is a father. You have role assertions like father of John Barry, which means John is the father of Barry. Also, John is not identical with Barry, and so on. So this is A box. These are actually specific statements about individuals. So things John and Barry are individuals. The T box is generic, okay? And they call it T box because it is terminological, right? So description logics are extremely well designed if you want to build terminologies. But because of the limitation, okay, for full-blown ontologies, they are actually not really adequate. So you have concept inclusions. For instance, here, all fathers are parents, okay, or concept equivalents, okay? Persons are the same things as humans. And then you have the R box, okay, which is for the relationships, like role inclusion. Everything which is a father of something is a parent of something, okay? Or the disjointness of roles, okay? So if something is the parent of something, then that something cannot be the child of that something. And there are many more of those examples there, okay? Assertions need to be interpreted as being about sets. Okay, so description logic is based on set theory. So we will see tomorrow, for instance, that the basic formal ontology is not based on sets, but is based on mereology. That's how things are composed, okay, what they are part of. Okay. Sets is a totally different mathematical construct. So, and then you have constructors like intersection or conjunction, okay? So male and parent, or the union of male and female. You have complements like not being male. And those things can be used in T-box axioms. For instance, father is equivalent, or being father is equivalent with being male and being parent. Or this statement here says that everything is included in the union of males and females. Well, it's actually not a correct statement unless you, of course, restrict it to animals or whatever, or human beings. Otherwise, it's not a correct statement. And this statement then here says that the males and females do not have an intersection. Okay, so the set of the combination of males and female is empty. A famous example of this is SNOMED CT. So I know that Irshad last week gave you a very brief introduction to SNOMED CT. SNOMED CT is one of the best formal terminologies that is around, despite all its limitations. It's the best formal terminology which is around, and it's based on now a description logic which is called EL++. Okay? So it does work with concepts. It has hierarchies, I think about 16 or 17 of them. It uses what is called attributes. They correspond actually with relationships. They use unique identifiers for each of their concepts and also for each of their terms. So what is nice about it is that they separate the terms from the concepts. Okay, and there is a formal way of combining it. A restriction is pure binary. All relationships are binary. Okay, so it allows for the following concepts. You can have atomic concepts, universal concept, your bottom concept. You can have singular enumeration, intersection and conjunction, and existential restriction. Okay. And you have those axioms here. C can be included in D, or C is equivalent with D. For roles, that the role P is included in the role Q, or P is equivalent with Q. And that C and A and R, A and B for concept C, role R, and individuals A and B. So that's all that you can express. Okay, you can't express negation. You can express disjointness of classes. You can say that in the combination of C and D there is nothing. Okay, but there is no disjunction. There is no universal quantification. There are no cardinalities. There are no inverse roles, and there are some role characteristics, but they are very limited. So in terms of logic, it's quite restrictive, but nevertheless it can bring you very far. So a couple of examples. This symbol here corresponds to the subclass. Okay, so abnormal nervous system function is a subclass of neurological finding. Okay, if you go into the details, you can see that they express it in this way, but they also have an expression in the OWL language, in the web ontology language. So this would how it be, and these numbers here, they are their concept identifiers. Here is another example, a little bit more complex, that says, okay, cleaning of an eye is included in a procedure on an eye, which has as procedure site a structure of the eye. Okay, and as an OWL axiom, it would be written like this. So there you see what is called an example of the existential restriction. You have equivalent class axioms. They are represented by this. Okay? So this statement actually says that the tonsillectomy is fully equivalent with an operation on the tonsils, which has as method an excision and as procedure site a tonsillar structure. And the OWL axiom is here. So what this actually means, that this is rather interesting. So if you know that a certain procedure is a tonsillectomy, okay, then you can deduce that all those things here are true. And the opposite is also true. Okay, so if you know that a certain operation was on the tonsils using this method and using this and with this site, then you know that it is a tonsillectomy. Okay, that's what these things here. Statements like this is normally are called fully defined. So the concept of tonsillectomy is fully defined.
Dr. Kusters, could I ask a question on the
Yeah.
Does this then imply that the only operation on tonsils is tonsillectomy? Because the operation on tonsils can't be a larger set if you have the equality, right?
Well, yeah, but it's the method here, right? So the method is excision.
Oh, I meant the equivalent class is the tonsillectomy and the operation on tonsils.
Yeah, but you need to read that together. So
Oh,
the equivalent is not between this here and between operation on tonsils. It is between tonsillectomy and this entire expression here.
okay. I see.
Yeah.
I see. Thank
Yeah.
you.
Other questions? No? Okay. So you can have also multiple axioms. Okay. So your product containing alectinib in oral dose form is totally equivalent with this expression here. But in addition, it is also included in things which are medicinal products and which play the role of antineoplastic treatment. Okay. So this is not equivalent because there are, of course, many medicinal products which play this role and which are not containing alectinib. Okay. So here in this case, it goes only from if you know this, you can deduce that. But if you do know this, you cannot deduce that. Okay. While for the equivalence here, it holds in both directions. There is also something like a general concept inclusion, where they actually say, okay, in this case, you see that secondary osteoporosis is included in osteoporosis. This one actually says that osteoporosis, which is such that the finding site is a bone structure and the causative agent is a drug or medicament, okay, is a secondary osteoporosis. So in this case here, you may only read it from here to there, okay, from this side to there. And if you have this, you may not conclude that this is the case. That's what they call general concept inclusion. So in general, characteristics of web ontology language-based description logics, so they are actually ideal for fixing the terminology of a domain. Okay, so that's why they are built around constructors. So you can actually construct your terms in a logical way. But of course, you can construct also nonsense. It's perfectly possible to design a terminology for Klingon, right? Actually, people do that, right? So, and for good reasons. Or if you want to design a computer game, okay, with different kind of monsters and weapons and this kind of thing, and you need to keep track in the game of what kind of weapons are able to destroy what kind of monsters. Okay, you need like a logic behind it. So with DLs you can do that. That's very well, I will not say easy, but if you know your DL, it's very doable and straightforward. Okay. DL reasonings can also detect contradicting definitions, and they can classify terms automatically. So if you want to build, if you have a huge amount of terms and you want to classify them, manually is almost not possible. Okay, so when you use DLs, you give your appropriate definitions, and you do that adequately in the right way, then DL can classify the terms for you, build your hierarchies automatically. Okay, but of course that is only if axioms are used of a sort that the reasoner can work with. Okay? And one of the things that take, for instance, protege with the different reasoners that you can build in, many users do not seem to understand that it's not because you write axioms, right, that they can be read by any reasoner that you are using. Okay, so the reasoner need to be designed for a specific description logic, and you need to use in your axioms when you are using protege, you need to stick to the description logic for which you have a reasoner. If you don't do that, then you get nonsense. And believe me, there is a lot of nonsense around in so-called ontologies vetted by means of description logic. So what is the advantage of the description logic? So here is an example. So it is asserted, for instance, in SNOMED CT that a cholangiocarcinoma of the biliary tract is equivalent to a disease which has as finding site a biliary tract structure and an associated morphology, which is a cholangiocarcinoma. Well, if you apply the description logic reasoner, then the reasoner infers, okay, that a cholangiocarcinoma is a malignant adenomatous neoplasm, and that it is a malignant tumor of the biliary tract. Okay, and this is exactly how it works. So if you are an author or an editor of SNOMED CT, and you say, oh, we don't have the concept of cholangiocarcinoma of the biliary tract in our system yet, and doctors need that. Okay, then if you write this definition here, okay, then the system for you will automatically place it in the right hierarchy, as you can see here. What are the drawbacks? It's based on non-defeasible logic. Okay, so there are no exceptions possible. Okay. Another one is you cannot represent classes of classes. So you cannot reason about classes. You can only reason about individuals in those classes. You cannot make statements about those classes. And what we see quite often is that authors, they know what they want to get as a classification, okay? But they don't get it unless they tweak the axioms in such a way that they get the outcome that they want. But thereby actually ignoring, okay, the open world reasoning that is applied by description logic. Also, description logic works open world, not closed world. So if you want to use protege or you want to use description logic, please read this paper by Alan Rector and friends on Beyond Gruber, Ontologies in Today's Biomedical Information Systems and the Limits of OWL. Okay, it explains it nicely, the kind of mistakes that are made, what to avoid, and so on. I really, really recommend this one. And for sure, you need to remember this forever. Okay, I read it for you. The words ontology and ontological, the web ontology language OWL, and the description logics on which OWL is based continue to cause confusion. So these are statements that are made in that paper. Description logics and OWL are major advances for representing logical definitions of terminologies. However, they are severely limited in representing other kinds of statements. As a result, their standard semantics is often ignored or distorted with unintended consequences. Okay, the bioportal is a prime example to that for that proof. Pick whatever randomly and you will find mistakes. There is only one ontology that I have found, okay, which has no problem. Well, ontology, it's in the bioportal, so it's called an ontology. I wouldn't call it an ontology. I would simply call it a list. So why is there not any mistakes in there? Simply because it doesn't have axioms at all. It is a long list. It is a long list of terms that are used by the in the dictionary of the American Psychological Association. Okay, all the terms are things, and not a single axiom. The only one we just not have a mistake. I'm not going into the details here, but when you see papers, okay, and this is from a paper. Okay, where they make those nice schemas and pictures of protege, guaranteed by just looking at the figures you find the mistakes. Sometimes I wonder how it is possible that those papers get accepted, or they must have been read by reviewers who don't understand OWL but find it nicely colored and arrows and whatever. But there is nonsense. Look into the details when you get the slides. It's too small here to show it to you, but it's full of mistakes. Okay. Another indication is when they start to tell you, okay, how many object properties there are, and I mean by numbers, right? Like this 106, 20 data properties in that. Also, immediately you know, oops, they have taken one or other description, like the protege system, loaded it up. It gives you how many axioms there are, but they never tested whether the axioms work, whether there are consistencies or whatever. And so on. You see things like two entities, for instance, persons and race, and then the relationship has race. If you see an ontology, okay, where most of the predicates are of the has X forms, you know it's not well thought of, okay. In this case, it's even explicit. So they write, for the interrelationship among factors, the main object property is relates. For example, occupation relates some exposure to carcinogen and pathogen was used to show the relationship between occupations and possible work-related environmental exposure. Okay, you cannot express possibilities in description logic. The things is for all, some applies. You cannot use for some. Okay, so there you know already, okay, it's not really an understanding of what is there. Here's another example where they started, try to use BFO and the ontology for general medical science for whatever purpose. And now you see here entities like, for instance, the disposition, disease that comes, disposition comes from BFO, disease comes from from the ontology general medical science. Then you have diabetic complication, that's their own thing. Then you have acute, and then you have allergic reaction. So what they are actually saying here, that every allergic reaction is a diabetic complication. Okay, if you get stung by a bee and you get an allergic reaction, then according to this ontology, you have a diabetic complication. So that is, of course, bullshit, right? So please, if you build ontologies and you want to use an already existing ontology, check it carefully, very carefully, or your ontology will be nonsense to the same extent as their ontology is. Any questions?
Yeah, I have a question about SNOMED specifically. You called it multiple times a terminology and not an ontology. And I'm wondering, what are the implications of SNOMED not being a realist ontology?
Well, it doesn't represent reality. What it represents is how doctors work with their patients and report their findings. For instance, one of the principles in the BFO is that, in SNOMED is that diseases only exist when you find it. So the notion of the fact that the patient can have a disease, right, which has never been seen, and I don't mean an unknown disease, okay, but has never been seen, that cannot be represented in SNOMED CT because it can only be found. I mean, that's their basic principle. Now, for doctors themselves, it doesn't really matter, right? Because it is the case. I mean, they cannot come to know that a patient has a certain disease and make a diagnosis when they don't look at it, okay? Doctors are not interested in patients that they don't see. So it is oriented around the clinical practice. And in that way, those philosophical considerations don't really matter that much. But the problem is, of course, if you forget that aspect, and then you are going to say, oh, we can use SNOMED CT to do scientific findings in the domain of medicine. No, you cannot, okay? Because the ontology behind it is flawed. Flawed in the sense that it doesn't matter for clinical practice, but it really matters for science. Does that answer your question?
Yes, it does. Thank you.
Okay. But that said, once again, so I have studied SNOMED CT for now over 30, 40 years, 30 years. It is actually the only one that I have found worthwhile critiquing. Okay. So people might think, if you read my papers, that I'm an enemy of SNOMED CT. No. I critique it because I want to get them to make it better. They are pretty close, okay? And despite the mistakes, they are pretty close. The only thing that I don't understand is why don't they make it realism-based? Okay, it would advance science way better. Anyhow, common logic. Let's look at the last one, because that gives then the nice segue into our third class on Thursday. So common logic is a family of first-order logics, and they have a common abstract syntax and model theory, and they use an XML framework for encoding and transmitting it over an open network. So the common logic syntax is very relaxed in the expressions that it allows, and in some ways it goes beyond classical first-order logic. Here is a link to the standard that you can read what it is about. So how does that actually work? Okay, so imagine that you have that you want to represent in common logic that John is going to Boston by bus. Okay, so we would express that like this. So there exists, well, one of the ways that you can express this based on your specific ontological commitment would be this. So there exists an X and a Y. So exist here is the existential quantifier. X goes, and John is a person, and Boston is a city, and Y is a bus, and agent, and there is an agent of John, the destination of the agent of X, that's that going here, right, is John. The destination of X is Boston, and X inst Y, what would that be? So go, I don't remember what the inst exactly is here.
Instrument.
Oh yes, instrument, right. Good, thank you. So I use the color coding here to identify what are the quantifiers, the variables, so the X and the Y, the predicates, the individuals, and then the connectives. Okay, the only connective that is used here is and. So this is a big statement with all ends. Okay. So in BFO, which we should look at tomorrow, BFO is axiomatized in Cliff in first order logic using the common logic representation. So you have predicates like human being is a universal. Werner is an instance of human being in the year 2002. This color in here is in that ball, and so on. And I use the same colors here. So if you later look at the slides again, okay, the same color coding as in here. So you see what the individuals are, what the predicates are, and so on. You have quantified constructs. Okay, for instance, there exists a time that Werner is an instance of human being. Okay, or for all times, if X exists at that time. You have negation, like it is not the case that object and history are identical. Or there does not exist a time such that Werner is an instance of quality at that time. So what is important here is that you see in these statements we use time indexing. Okay? And that allows you to express things in relation to time. Okay, so because if Werner would be referring to me, okay, then it is indeed the case that there exists a time that I'm an instance of human being. Okay, that's already now for 67 years the case. Although some of my students claim that I'm not a human being, but that's another story. But I will not continue to be a human being. Okay, in a couple of years I will be a cadaver. Okay. But this statement nevertheless remains true, okay, because there was a time that I was a human being. There will be a time that I will be a cadaver. You can make constructs with and or. For instance, it is the case that Werner was a human being in 2002, and it is the case that he was a human being in 2003. Or this color in here is in this ball, or this color in here is in that ball. Okay. You have implications. For instance, A is an occurrent part of B if and only if B is occurrent part A. Or if there exists a time that A is an instance of an occurrent at T, then A is an occurrent part of A. So advantages of using full and Cliff in this way is that it allows for precise, unambiguous, and machine processable description of what one ontologically commits to. Okay? These things can be parsed very easily, right? It's like list expressions like you use in the programming language Lisp. Very easily to parse. So an example from BFO 2020 is this one. For all the times, if T is an instance of a temporal region at T, then there exists a universal. Okay, I'm translating it. No, let's do it literally. Then there exists a U and a Y. for which it is the case that Y is not identical with T, U is a universal, I is a particular, and I is an instance of U at T. Okay? So actually, in natural language, that means at all times there is at least one particular and one universal that is instantiated by that particular. So that is a very precise statement about the ontological commitment of the BFO. Okay? At all times, there is at least one particular and one universal that is instantiated by that particular. It's machine processable because the syntax can be checked by a parser. And I will demonstrate that on Thursday very clearly. It allows for transformations to other formats, such as Kowalski rules. Okay? So there are 5 forms of Kowalski rules. So you have the if-then rules. For instance, A and B and C, etc., imply P. Or, unconditionally, P is the case. You have what they call if-then-or rules. So like A and B and etc. implies P or Q or and etc. Or, as with the if-then rules, it is unconditionally the case that P or Q or etc. And then you have falsehood rules. Okay, so if A and B and etc. is the case, so that's false. This actually means it cannot be that A and B and C altogether are the case. So these are 1, 2, 3, 4, 5 different Kowalski rules. So I talked already earlier about the Horn logic. Okay, so a Horn logic is restricted to those 2 rules here. Okay, whereby A and B may be true or false. Okay, so you can have not A or not B here in this expression, but P must be true. You cannot have as a conclusion that something is not the case. Then you fall outside the Horn logic. You can simplify actions. Okay, that's the biggest advantage. For instance, there is the BFO axiom that no role changes type during its existence. Okay, so the axiom is written like this. So you see with 1, 2, 3, 4, 5 quantifiers and a number of variables and so on. Well, if you convert to change or transform this axiom into Kowalski rules, you get actually 2 different rules. So one rule says if E is an instance of D at A, and E is an instance of D at C, and A is an instance of a role at B, then E is an instance of role at A. And it also gives you the second rule. So one axiom is split into Kowalski rules. If you study those rules carefully, now you can see that you can remove redundant literals. So the C here doesn't do any work in this rule. And the B here either. So you can remove them, those literals here. Okay, so you are left with this. And then if you compare both, now you can say, okay, we can rename those things. You see the similarity in those 2 expressions here, where you have a B here and a C here. But you don't have a B and you have a C. What you want now is can we rename these variables in such a way that there is a more analogy with what we have on the left side? And you can do that, and you get this. And if you then look, okay, then you can simplify it further. Then you just get this one here. Okay, this is the case, and that is the case. And then you can transform that back to Cliff, and you can rewrite your axiom in this way, that for all EDBA, okay, if E is an instance of D at A, and E is a role, then E is an instance of role at A, and E is an instance of D at B. Okay, so you actually, an axiom which was written quite complexly can be completely simplified in this way. It's totally equivalent. Okay, and that it is equivalent can indeed be proven by using your first-order logic reasoner. And again, we will demonstrate how to do that on Thursday. So you can use those Kowalski rules to have processed by relatively simple logic programs to test satisfiability, to develop models, to do term expansion, rule-based optimization, and so on, as I will demonstrate. And that concludes my presentation for today. Are there any questions? I hope I didn't overwhelm you too much.
I'm curious about the difference between decidability and machine readable, parsable. Um, it sounds like you said DLs are used because they are decidable, but that common logic is like what would be the shortcoming of or what would be the issue with using like a more formal logic or a common logic?
Oh, I think those are two different aspects. Okay, so but maybe I didn't accentuate it too much, but you have the notion of a common logic, which is that idea that a different kind of logics, okay, should be able to be expressed in one specific syntax, okay, and that there now would be a reasoner that can deal with that, okay. So for common logic, there is no reasoner yet. So a semantics has been defined, but there is no reasoner that works with it. So what you would do is to limit, to use the common logic interface language, CLIF, okay, as a vehicle to write in a logic like first order logic, okay? And that's what we have been doing with the BFO. So there are a couple of elements that in common logic you can do. You can use common logic to, for instance, write a second order logic if you quantify over relationships. Okay, we simply don't do that, okay, because there is no reasoner for those kind of things. Now, readability has to do with the syntax being formal, whether there is a clear grammatical way of analyzing sentences unambiguously. Okay, that's what the part, that's the difference between computer language and natural language. Okay, there are English, for instance, is ambiguous. Okay, now for us human beings, it is not a problem because usually on the basis of context, which is not explicitly set, okay, we understand what is said. I honestly must confess, since I'm started to work with ontology really deep in logic, I start to have problems with understanding people because whatever they say, I immediately see the ambiguities in there, and then I need to ask for clarifications. And I lost once a girlfriend simply for that reason. So why do you not understand me? Okay. Well, for a computer language, the syntax is formal. Okay. So you can write, for instance, what's it called there? The name escapes me, but you can write a simple algorithm that analyze that language and get the correct interpretation. Okay, two different aspects. Decidability has to do with the logic. Okay, is it possible to make conclusions in a reasonable amount of time? Is there a methodology to do that? To inform, to be able to assess whether a given expression falls within the logic? That's decidability. Whether it can be readable, okay, is whether you can parse the syntax and work on there.
Is there a problem with common logic not being decidable?
Well, no. Why would that be?
I guess I'm wondering why people would use web ontology language if it's less expressive, and like what would the benefit be to having something be decidable?
Well, you can express things more to the full extent. So you are not limited. So first order logic is limited as well, in the sense that you can't quantify over relationships, right? Over predicates. You can't quantify over there. So that is in itself is a restriction what you can do with second order logic. Description logics, they removed quite a bit of first order logic specifically to make it decidable. So in cases where what is important is the decidability, okay? So if you have a system like SNOMED CT, I think there are by now 400,000 concepts or so. If you add one, okay, you would like to have a reasoner that is able to do that in a reasonable amount of time, okay? I believe last time that I saw a paper about SNOMED CT, if they produce a new version, I think the classification of it takes 3 hours, which for the size, okay, for the size of the terminology it's actually very good, right?
Mm-hmm.
But if you wanted to use, for instance, on the spot, let's say a doctor wants to use what they call a post-coordinating expression and see whether it fits in the logic, that's a totally different story.
Okay, thank you.
So, yeah, it is a matter of what do you want to express and how fast do you want the reasoning. And those two, they are actually, if you want more of the one, then you need to give in on the other.
Mm-hmm.
That's it's like between time and space in databases, whether you include redundancy or not. Other question? No, okay, thank you very much. So I'll hope to see you again on Wednesday to look at the realism-based principles, and then on Thursday when we are going to work with Cliff, with the parser, with the reasoner, and so on to give a demonstration on how to build ontologies the realism-based way. Bye-bye.